Hey everybody, my name is Jake. I'm assistant professor in information science at Drexel University. I do a lot of work in NLP, but my training's in mathematics, so I'm sort of all over the place in terms of my background. And today I want to talk to you about what I would classify as a core NLP task that can be used or implemented to enhance more or less wherever you use words as tokens or features in your text analysis down the line. So first I want to motivate that a little bit and go back to ground zero and just talk about what bag of words is and why we care about it and what are its limitations. It seems to be relatively pervasive. And then we're going to talk about how we can improve that in a small way by somehow getting meaningful phrases instead of words as features. And we'll talk about what meaningful means. And then just to show you some ways that I've thought about using it in the past that are hopefully going to motivate you to consider how to use it. An example implementation where we're going to track political action on Twitter. So as I mentioned, I'm just going to talk about what is bag of words here for a second. And the idea is to form some sort of a weighted distribution of words in your obliterating context and just counting multiplicity, or you're weighting in some other capacity, TF-IDF, or word embeddings, or something fun. One of the important things is that you're losing a lot of details of context by reducing to multiplicity. So how would you conduct the construction of a bag of words model? First thing you do is you tokenize. You count occurrence frequencies, maybe you go somewhere else from that, TF-IDF, maybe you modify that some other way with word embeddings, and you maybe get rid of stop words, whether it's by downweighting through TF-IDF, or you just throw out stop words that you have in a list, whatever your procedure is. That's the general process. And so let's just look at this in example. So you have your example, which is the title of this slide, and the first thing that you might want to do is to break this into tokens. So let's take in bag of words as an example, is the sentence that we're looking here at. So I've got some tokens. Let us take in, and you'll notice I leave space as a token in addition to other punctuation characters. I've got strange reasons for doing that, which maybe I'll talk about going forward, but also I'm going to use them here in this model that I present to you, these space characters and other boundary features. Next step would be to count them up. So how many times did each of these things occur? You might throw out space and all these other things, and you wind up with just your salient words, so you think that bag is important to express the meaning of this sentence or whatever else. But you get rid of words like the or in or determiners, prepositions, delimiters, whatever else. And you're left with a couple of words that you hope are somehow indicative of the meaning that is present in the original document. So why would we use bag of words for text analysis if it's just obliterating all of the context? You'll notice that we get rid of the order here now because we can't assume that it's anything but alphabetic at this point. So what's nice about this? Well, it's fast. That's the first thing, probably, is that it's a really quick way. You parse a document character by character. You're going to be dealing with a much higher multiplicity. Things move a lot slower. It's reasonably simple, especially when you're dealing with something like English language, where you can just say, okay, split by space. That's a reasonable delimitation for English. Maybe there are a few assumptions, maybe they're actually relatively grave assumptions, but it seems relatively intuitive since we like to look words up in dictionaries, so it doesn't seem like we're assuming much. And I guess maybe the piece that's under the hood there is that we do have this belief that words are these minimal units of meaning. They are the minimal semantic units that we can look up and get the right meaning. And that's really the issue that we have here, is maybe context. So how could bag of words be better? How does it get better? I guess I'm taking us back to tokenization as a core procedure to enhance for text analysis. So at each step, so maybe tokenization into words doesn't actually produce minimal semantic units, and maybe that's a core problem in text analysis. Maybe it would be better if we provided minimal semantic units to our favorite machine learning algorithms as opposed to things that we sort of feel without justification that they might be, and they are often. You might love to use word embeddings, you might use TF-IDF, you might want to do something better for frequency. That's really not what I'm approaching here with this talk. You can still do all of those things with what we're going to produce here today. And the third thing is that, well, maybe some words are only salient in context, so you won't want to throw out stop words, but maybe sometimes those stop words are actually relatively valuable, depending on where they appear in your sentence. Maybe they should be a part of something that is idiomatic or whatever else. So we're going to work on making the first step better, and by virtue of that, we're also going to make the third step better. But as I mentioned, we're not going to focus on the weighting portion of this. That's a different conversation. So instead of word tokens, our goal is phrases. And what constitutes a phrase here is one of the primary questions. Is a phrase an n-gram? Is it something that's just sort of a sliding window? Or is it something that has some sort of a semantic embedding that we can rely upon and look up? So what's a multi-word expression? That's in my title. That's my important thing that I'm trying to get across that we want to find. Multi-word expressions are semantic units that are minimal. There's some kind of irreducibility going on where if you break down that expression any farther, then you will destroy the meaning of what's going on there. Sometimes that semantic content is somewhat compositional, but it might be relatively dense still. Other times it's entirely unapproachable from its constituents. Intuitively, you just take multiple tokens that form an idiomatic whole, but sometimes it's not just idiomatic expressions that you're looking for when you're looking for multi-word expressions. This covers things like named entities, places, people, etc. But the bottom line is that multiple tokens, multiple words are taken together, and we're sort of going to get a little fuzzy with what we're referring to as tokens from here on out. So let's specify the task. Why is this segmentation and not identification? You hear about named entity recognition, trying to pick out the named entities. Why are we doing segmentation? And that's because our goal with multi-word expressions, segmentation, is comprehensiveness. We're trying to get all of the different flavors and types of multi-word expressions as opposed to just verb phrases or just getting out the named entities and things like that. And as a result of that, you're going for all types of MWEs. This is an example of what one segmentation would look like. It's an example from one of the, or probably the best data set that's out there on comprehensive MWE segmentation. The point is that you do get a segmentation of the minimal semantic units. It's really not the MWEs that you're segmenting, since sometimes the minimal semantic units are the words themselves. It's actually the fact that you can trust that the word wife actually means what you think it means, and you can trust that the phrase taken in actually means what you would look it up to mean. And yes, multi-word expressions can be gappy, which means they can cross on top of other multi-word expressions or terms or relatively complex stuff going on here. But the point is that you can take taken in or oil change, and you can look it up, presumably if there is a dictionary that contains these items, and there are some. And the gappiness is a little bit confusing there too. So we've got a named entity inside of a verb phrase, and there's another fixed expression that just has some sort of grammatical irregularity as opposed to a change of oil, it's oil change. But this is generally the picture of what we're looking for. So why do we care about MWE segmentation? Why am I trying to motivate this? I brought up bag of words to begin with, and I said we're going to worry about the tokenization step. But if I haven't beat it in enough, the semantic irreducibility framing is really what we're interested in. It highlights idiomaticity and non-literal meaning. It reduces polysemy, so if you do have multi-word expression, there might be fewer choices if you're trying to determine the semantics of your multi-word expression versus the constituent words. And if you do manage to somehow construct a perfect MWE segmentation algorithm, then you will, by virtue of that process, extract all of the named entities, so it's great for information retrieval. But how can this improve bag of words is really what we care about here today, because I want to use this as a motivator for how you can really take any sort of text analysis pipeline and improve it by just feeding in multi-word expressions as opposed to words at the start. Well, let's imagine topic models with, instead of words as input, you have the semantic irreducible phrases. That means in your lists that you're trying to interpret upon output, you immediately get the semantic objects that you can look up and say, what does this thing actually mean? You don't have to go down the list and say, okay, well, this word's probably co-located with that other word, but I have no evidence for that. Inputs contextualized to text-based classifiers. You talk about naive Bayes. There's this assumption that your words are independent of one another, but if they really are members of multi-word expressions, those are fixed expressions where they're actually quite dependent. So that contextualization is quite important. As mentioned, for information retrieval, it would be great if you could somehow have all of your named entities, but that's in a perfect world. And I've sort of covered this one a little bit with contextualization, having more independent features. So let's go back to our example and look at bag of words. What would it be like if we somehow had that multi-word expression segmentation to begin with? In this case, I've used the expression take in and bag of words. Those are both multi-word expressions, and you probably not get the meaning right if you had to look up the word bag, or you have to look up the word in to figure out what's going on. Somehow we're rocking this model, which is metaphorically a bag of words. So here is what you would result in with your bag of words model. Space appears fewer times, the word in only appears once. And so if you, once again, you can get rid of all your stop words, do your weighting, all the rest of that. Now you get rid of the word in, but you still have the word in somehow embedded in a more meaningful expression that you can interpret, likewise bag of words, etc. So how are we going to segment MWEs? This is the target, so what's the method that I'm proposing? And the method that I'm proposing is a pet of mine that I've been working on since I was working on my PhD a couple of years back. And this is its recent incarnation. And the approach relies on the notion of boundaries. So I'm actually utilizing the function of some of the most forgotten content in text analysis. A lot of times we split by space. What does that do? It wipes it out. It's completely out of the picture now. I'm saying let's use space as a feature along with all these other boundary characters like period, comma, vertical bar, whatever you want to call not a word. So I view a text as an alternating sequence of words and non-words. Sometimes these things are null. They just aren't there. You take a contraction, there's a boundary in between it, but I'm calling it the null boundary. So anything that is not defined as words, so then you are then left to define what are words and what are non-words if I want to conduct this algorithm. And for me, I just define a set of word characters, and anything that has a word character is a word. That way I don't have to rely upon a dictionary. So as I mentioned, boundaries include things like space. It can also be null. So each boundary, those are our features for text partitioning. If you haven't gotten the picture yet, just getting to a tokenization now, I'm proposing as a supervised machine learning process. But my boundaries are my objects that I would like to somehow make some prediction of, and I want to predict what state they're in. Either are they in a binding state or are they in a breaking state? The boundaries stick their adjacent words together through themselves. And this is but bear in mind that by proceeding with boundary word, whether it's null or a real boundary, you're actually preserving the exact structure of text when you're going through with this procedure. You're not forgetting where the space was, you're not forgetting where the commas were. You get the exact replica in the tokenization of your text. It preserves the original content completely. So to me, a gold standard looks like this. It starts with a word boundary tokenization, where I have the states resolved by some expert annotators. So those are the S's that are there on top of the boundaries. They might be zeros, they might be ones, and they might be sticking together or breaking apart the adjacent words. And what I do with a gold standard, I do something very simple. You could take a gold standard like that and try and predict the states with a neural network or a deep learning algorithm, whatever you'd like to do. The goal is to predict the states and the boundaries. For me, I've just taken and done something very simple here and done a count-based method. I'm measuring the frequency at which word boundary word patterns in particular states occur. So how often does the word boundary word pair result by the types of words and the types of boundaries underneath those positions? How often does that word boundary word pair appear in the binding state? That is my empirical partition probability that I'm going to use as a way of deciding whether or not, when I go out in the real world, non-gold standard data, whether or not to decide to stick two words together. Bear in mind that also this reduces the complexity of deciding when a phrase should be a phrase or a multi-word expression, because you're not doing this you're not deciding about words multiple times. You're deciding each boundary in between words independently. So if you have n words, there's n minus 1 decision points, and that's it. It's linear in the number of words. So it's relatively efficient. So returning to our example, what would this look like? My goal would be to resolve this state for the example that we had. Let's take in bag of words in an example. And you can see that this is a null boundary right here that I would like to predict in the 0 state, whereas this is boundary as space that I would like to predict in the state 0, boundary as space in the state 1. That's the goal. And I would have to, from my gold standard, somehow determine how often I saw the boundary space in between take and in the binding state. That's just the way that I constructed this. Like I said, you can take in a gold standard, look at the states, whatever else, it's your training data. You can apply a deep learning model, something like that. But for me, it's simplicity at this point, just to see what the value of this model is, really centered around boundaries as opposed to words for the purposes of segmentation. So if you haven't realized, this is a supervised machine learning problem. As I've said, we're starting off, before you even enter into the rest of your text analysis pipeline, I'm starting out with a supervised machine learning problem. But that's what you're doing as well when you're doing part of speech tagging, so it's not that strange. And it's important to note that many MWE patterns fall outside of training data. There's a lot of different types of named entities out there in the world. You might have some relatively consistent patterns that exist with verb phrases, but named entities are open classes, and those are very difficult to really approach. The other thing is that there's lots of false positives out there, so getting your precision up is actually relatively difficult. So here, this one is a conflict of potential MWEs because takeout and out there are both idiomatic. And if you just want to decide whether or not to bind takeout or out there, you wind up with a 3-word expression that is not defined. So that's why I offer 2 enhancements with this package. One, where you can segment according to part of speech patterns, so you do pick up on proper noun, proper noun, proper noun. Hey, look, that pattern probably indicates a named entity. And I also prune multi-word expression candidates with an algorithm that I call the longest first defined. The algorithm is the name. It just clips off candidates that it sees first that are actually defined in some dictionary or record from left to right. And for English, which is where the majority of the good data comes from some folks at CMU, it turns out that text partitioning outperforms nearly all other algorithms, and this includes perceptrons and conditional random fields, and this has been a shared task in multiple venues, and this is a really simple model that I'm proposing here. So maybe you could enhance this model with some other more complicated decision criterion. But the point here is that even just in this simple formulation, we've got the state-of-the-art algorithm for NLP, and this is not a deep learning model. And this method is sufficiently general to be applied to other languages. The issue with data presently and other languages is that the MWE data sets are not comprehensively segmented. They're just verb phrase MWEs generally, and this is a segmentation method. This is not about an identification of MWEs, so performance is relatively lower at the other languages, though it still is state-of-the-art in some of the other languages. And I've tested this in 19 other languages, but all of those languages do use space and punctuation and delimiters as opposed to other languages like Chinese, which generally don't use space as a delimiter. So, can you get the software? Yes. I'm not a software developer by training. This is something that I've been figuring out along the way, so if you find bugs, please do let me know. But my goal is to make something that's fast and functional for you guys if you would like to use it. So please do check it out. I've got a very slim tutorial here. Doesn't want to load. But if you just want to see what it does, maybe this is a bad idea. Just keep going. You can download the software just by doing pip install Partition if you would like, and I would be happy to help any of you to get used to using it here today as we get into our make sessions. So, moving along that line, I want to show you a research project that where I used this software along some of the motivation lines that I spoke about in earlier slides, and that has to do with identifying political actions on Twitter. So the goal is to focus on political action in social media text, and some motivation in case some of you have never heard of Twitter. People say lots of mundane things, but the idea is maybe sometimes they say some things that are important too. So for those of you who are unfamiliar with Twitter, it's actually up to 280 characters these days, not 140, but most people still use 140 characters. It's just when they really need it turns out, and that's why Twitter decided to go with it. And sometimes these messages can be geolocated, which has already been a point of discussion yesterday. There's lots of people using it, so that's important too. So let's just talk about the data set of location tag messages here. Back when I was a student, me and a fellow student, we set up a Spritzer stream, so that's their 1% public API, and we collected tweets for a year that were geolocated. And over that time period, the 1% API aligned relatively well with our estimate that 1% of all tweets were geolocated. So we got a reasonably complete sample of the geolocated tweets that were out there. And over that year, we collected 600 million geotagged tweets. And in the stream, I also enriched that data with polygon tags. So we knew from the latitude, longitude, which country, county, state level equivalents those tweets individually came from. And as a result, we had a nice information retrieval system. This is what it looks like. You have the timestamp, you'd have the polygon box that is referenced according to GADM shapefiles, and latitude, longitude, and then the text. So we knew where tweets came from, and we knew when tweets came from. But 600 million tweets is way too many tweets to go through by hand to expect some portion of them to be associated to political action. So how did we filter those down? For that, we used the university license, this university's licensed AP Images database, which is searchable by keywords like protest. And along with the images, you get captions, and inside of those captions, those are metadata tags that you get. So places like city and places like time. And as a result, we were able to use these images and their metadata information to put a pin in our data set, both in space and time, set a radius, and collect tweets that happened near wherever these images happened. And that was a way to filter down from 600 million tweets to about 50,000 tweets that were very rich in political action. We're building a supervised machine learning classifier for political action. So what's our framework for political action? Moving a little bit more quickly, we had 4 different types that we identified. We were interested in groups of people, individuals, and we were interested in some variation in how the individuals exercised power. Were they forceful or were they peaceful? And so this gave us a 4-way framework for identifying political action. So we hand-coded lots of tweets. I hand-coded a lot of tweets. And, but a tweet can represent many different action types depending on how discussion is being made. So this is an example of what some of our codings are. So for example, someone saying, I hope they riot. Silent protesting apparently doesn't make much of a scene. That's representative of several of these different tags because they're talking about silent protesting. They're saying, I hope they riot. And individually, they're inciting a riot. So we've got singular force there too. So our methodology is stick to the simplest method possible. Why? Because it's decomposable and we can interpret it and turn it into a diagnostic tool. So naive Bayes is great because multiplicativity turns into additivity when you take a logarithm, and a naive Bayes classifier is a sum of logarithms that is the same classification as the probability that you get as output for a posterior naive Bayes classifier. And that linear decomposition that you get when you decompose a naive Bayes classifier logarithmically lets you say how much impact did these individual words have on a particular classification. So along with that, we're clustering tweets geospatially and temporally to look at time series and clusters of political movements that were going on. So this is, over that time period, the New York climate protests. So there are clusters of tweeters all along Central Park, down Broadway and Columbus Circle. We have our output telling us how many tweets were classified in different categories over that time period, which is a small lie that I won't explain right now. And then the decomposed classifier that says exactly which words contributed to the classification in some particular cluster that I happen to click on in that time period. And you can see phrases that we get from our MWE segmenter, like Columbus Circle, any other good ones here, I'm not sure. But there's a couple other examples here. Central Park, names of places where you could then say, if you didn't have the map, because Twitter unfortunately doesn't geolocate the way that they used to, you could get some information on where these tweets came from, just as a result of the MWEs. We also did this in Ferguson during the BLM protests that were going on following the verdict of Darren Wilson. And this was during the burning down of the Quickworm. And you can see expressions like on fire, which happens to be a false positive, by the way, for the MWE segmenter. Unfortunately, these things happen. It is supervised machine learning. But in general, you can see the decomposition as being productive of salient terms. And one last example is from the Hong Kong democracy protests over that time period, because this was a global data set and we could point this tool wherever we wanted to. And you do get expressions like tear gas, which, by the way, independently, those two words might confuse a classifier. Somebody could be talking about crying because they're in such gastric distress. But likewise, we have here on the map the three. By the way, each one of these clusters is a Venn diagram that indicates the portion of tweets that were related to that type of activity, and this one is collective force, so this is violent protesting. So there was relatively violent protesting in the three core locations during the Hong Kong protests. One of them is actually a named entity here, Mong Kok, there. So that is also picked out by the Mwe segmenter. So interpretability for human output, non-confusion and context for classification. Those are some of the things that we like about MWEs. So there are some limitations to real-time application. We'd like to turn this into an interactive tool. We'd love to have all the data in the world. We don't. In addition to that, Twitter changed some policies that reduced the number of geolocated tweets that are available. So when you're looking at a public stream, you're not getting anywhere near as many as we were getting at this time period that allowed us to have this sort of resolution. So going forward, our problems are really trying to figure out where are we going to get more data, how do we re-engage Twitter users to start geolocating again, because this is a tool for them to organize. This is a tool for people to be heard that they're getting tear gassed. It's not a tool for surveillance necessarily, it's a tool for people to organize and get together and conduct some sort of a movement. It's not just surveillance. But all of that is really something that's in the figuring it out stage and not really going on live. And we also want to turn this into an event detection method. So if you organize tweets by actions, you collate them together, you do some sort of sentiment, you do some sort of reduction in terms of what do these things mean. Maybe we can turn this into an event detection algorithm. But anyway, that's all I've got here to say. There's certainly plenty more things I'd be happy to talk about if you want to pull me aside. Thanks.